Okay. So continuing with the surface water, we saw that the impounding reservoirs and that impounding reservoirs, though we believe that the water that has been collected over there, the dam, it is not contaminated, but the water that is draining from the catchment area, it may be contaminated because of the habitat of the people living there, or by the domestic animals, or even by the uh, wild animals. So it is very much prone to contamination, but still safer. Second rank in in safety to use when I mean when compared to other water sources. After two rain, second in rank. And then what is the next one? We saw the rivers and streams, which is very much polluted. We saw the this water is never safe for drinking until we do some kind of treatment, and that is because because this is the rivers and the streams. The people will be having a tendency to pour their wastewater, the domestic water, the sewage, the sullage, everything into it. So that may be getting polluted, and some sort of purification is happening, but still treatment is required. I think we have to start with this one, the second one, the tanks. So tanks in case of, which is another example of surface water. So the picture will be like this. It can be as open like this, and you see the kind of dirty water and what the people are doing on its surroundings, making it more contaminated. Or the tanks can also be like this, over to a very great height and completely protected. So both the ways a tank could be called as. So we see the features of the water in the tank. So tanks are large excavations in which surface water is stored. They are recipients of contamination of all sorts. You saw in that picture. They're full of silt, colloidal matter, especially immediately after the rains, because it is not covered obviously. All the silt and the colloidal and whatever waste materials, it will be running off to the older tanks may be full of aquatic vegetation because no one is going to clean it. Probably it is going to be a government property or a public property. So no people will be bothered about cleaning it. And every day the water will be added into it, replenished. So no one will be bothered about cleaning. Even that's the same thing happening over here also. The cleaning is going to be too difficult. So when for a longer time the water is being collected, it is going to result in growth of vegetation. Tanks are often used for washing of clothes, cattle, humans, cooking pots, all the washing clothes, dishes, animals, even children, everything happens over there. The children use it for swimming, and there may be regular defecation around the edges which will be washed into the tank at the next rains. And this regular defecation not by the humans, luckily, probably by certain birds. So they may be sitting here on uh, that corner area over here to drink some water, and then they may be buzzing or defecating, and then when the rain falls, it is a probability that the stool that matter, fecal matter may be going towards this water. Tanks are thus subjected to unlimited possibilities of contamination and are highly dangerous as a source of drinking water, even at the best of times. But unfortunately, the tank water is drunk without even being boiled, disinfected, or having undergone treatment of any kind, which is very responsible for sickness and death, particularly in children. So how we can improve the tanks? The best way is whatever that is causing a contamination, remove those things. And these sections actually, when we consider public health, it comes under the section of public health engineering. I don't have to go much detail, but little bit I am saying. So what could be the improvements? The edges of the tank should be elevated in order to prevent the entry of surface washing, to raise the edges, and not just to raise the edge, there should be something like a fence or an obstacle so that animals can't come near to those tanks. No one should be permitted to get into the tank directly. Children or adult or no one should be allowed to get into the tank. The weeds should be periodically removed. Even if it is a government project, the local people who are using it, they should be responsible, taking the responsibility and removing it periodically, or at least the government do it, something. The tank should be cleaned at the end of the dry season and subject the water for filtration and or chlorination, especially before using it for drinking or domestic purpose. So this is some news that I have taken, the Borneo Post 2020. So this was told by the Infrastructure Development Minister Datuk Peter Anthony, announced that a new storage tank with the capacity to store 45,000 gallons of water would be soon built in the village of Kapung Ungan. I hope it is pronounced like that, otherwise you know. But I don't know whether this is the minister even now. Probably last year the election had taken place and he had changed, right? Is he still the minister? You know? You don't know. No one is in politics, interested in politics. Okay, so anyway, I just kept that as a news.
Yeah, you kept that. Not
While
interested.
any, while
Keep
any,
changing. Keep changing.
even in India it changes. But I don't know because this was in 2020 during the COVID time around. So did he keep that because it was just to keep a storage tank? Did they keep or not? I don't know. I was just googling and then I found this news. Then going towards another surface water or surface source, that is sea water. So there are plenty of water, the plenty of sea water, but not a drop to drink. That's the situation. So this source is plentiful, but it has great many limitations. The most important limitation is the salt content and other minerals that is present inside the seawater. It contains 3.5 percentage of salts in solution. So before we use seawater, the thing is we have to treat the water by the process of desalination and demineralization so that the excess of salt and the minerals can be removed. And this is going to be a heavy expenditure. It is adopted in places where seawater is only the source available. Like over here, there should be more islands like that where only seawater is available. So they have to go through this process. Otherwise, there is no need. Even in India, I don't know whether you have heard there is a island, Lakshadweep Island. So it is an island actually, surrounded by all the sea. And my sister is living there actually. So they don't have any other water source other than desalinating the seawater. So they can understand that difference of water. Even when the water has undergone the process of desalination, still I have gone there. When we drink the water, we can feel that salty taste even after this process. So this was another news that I have taken. Malaysian students invent device that make ocean water drinkable for the sea nomads. So sophomores Benny Bay, Hume and Lu Sing Yang, Yap Chun Yoon, I think that is the way it is pronounced. They are the students from the Asia Pacific University of Technology and Innovation and won the top prize of 10,000 ringgit for its official entry to the international design competition. So that I mean they made a machine design actually to for this process of desalination and demineralization. The students came up with the device flotation concept after studying the needs of local community living near the sea like the Bajau tribe in Sabah. Now going to the third source, that is groundwater. So from where the ground is getting the water, obviously from the rain. So rain is the primary source. From that a little bit washes, not a little bit, considerably it will wash into the river streams from where we store it in the impounding reservoirs or the tanks. And then we have the groundwater which is also receiving the water from the rain. So the rainwater percolate into ground, constituting the groundwater. It is now realized that there is a limit to groundwater in the world. We should withdraw only quantities of water that can be renewed. Groundwater is the cheapest and most practical means of providing water to small communities. Benefits of groundwater. Groundwater is superior to surface water because of many reasons, and one of the few reasons is that it is likely to be free from pathogenic agents or microorganisms. Many of the microorganisms may not be there. uh, it usually requires no treatment because it is under the under the soil. So even the soil, the clay, everything acts like a sieve. That's what it is saying. The ground itself provide as a filtering medium. Now in the latest slides we see that how this filtration is taking place, the slow sand and the rapid sand, and then you will see the layers of gravel, sand, soil, etc. kept, so that the water that is coming out after getting filtered, it is completely filtered, or it has removed the impurities. So when the water is under the soil, the groundwater, the same what we do artificially in the form of a filtration system, the same thing naturally is happening under the ground. So it acts as a filtering medium. So there is no need of much treatment, but still it is very good to have the filtration process. The supply is likely to be certain even during dry season because it is in the groundwater. There is no fear or anxiety to think about whether this water source will be drying up in the summer season. May not be in Malaysia, but in India, I mean in Kerala, when we come to my own state, there is the biggest river, the freshwater river in Kerala. But this river will be getting, it is the longest and the biggest, okay. And when you see it in the rainy season, we have actually a railway line crossing that big river. So when we are going via train over to that I mean that river during rainy weather, we can see that the river is so full, so massive. But the same place we go in a summer season, we will wonder where the water has gone. We will only see the soil over there, and here there is some puddle of water, only that much in summer season, because the whole water get dried. And we always, I mean, I always used to wonder how it's possible. It is one of the biggest rivers, still how it get dried off. So like that problem that it may get dried off in the summer season, that tension or anxiety we don't have when it is the groundwater. Even during the dry season, there will be availability of water, and it is less subject to contamination because no one is going to go under the ground. But still there is a possibility. Still the contamination is very less when compared to that of the surface water. So, what are the disadvantages? We saw the list of the advantages. What are the disadvantages? Because it is under the soil, a lot of minerals can get mixed into the water. So, that itself is the one of the biggest disadvantage. The water will be having high in mineral content. So, when we taste, we will have that difference, that hard water taste or something. We can feel that. The salts of calcium and magnesium which render the water hard, so that taste will be there. And because it is groundwater, it requires pumping or some kind of arrangement to lift the water from the underground. The usual underground water sources are wells and springs. Wells have been classified into shallow and deep wells, dug and tube wells. So this will be like a dug well, and if it is not gone so deep, we call it as a shallow well. You can see the length, and if it is gone deeper, it is called as the deep well. And this is what called as the tube wells. And while I was going through the Google, I saw that this was perhaps there in Malaysia in very early, maybe before 1950s. and after Britishers left, it also closed down when it became an independent country. And now almost all the houses in Malaysia is being supplied with what is that? The pipe water. That's what I read. So anyway, these are the different types of one type of groundwater, that is the wells. So going towards what are the difference between shallow and deep wells. So shallow wells tap the subsoil water, that is water from above the first impervious layer in the ground. So now we need another diagram to see this. Uh, so it may not be that clear because it is a picture that was taken from the textbook. So you see there is a deep well and there is a shallow well. Now this is under the ground. What is the different layers? The earth strata. So just under we have a water table and then a pervious strata. So now just remember your geography classes when we learned about the earth crust everything. We know that the earth layer has got, I mean earth has got different layers. Sand will be there, then there may be clay, then there may be some limestones, gravel, rock, all these layers. So when it is something like um, a layer with this sand, gravel, clay, etc. It is called as pervious strata. So water will be collecting over there, and it is called as that area is also called as first aquifer. Then there is an impervious strata through which water cannot be passing through. It will be the layer of limestones and all. And then after to that there will be again a pervious strata, and this is called as the second aquifer, and then follow to it impervious strata. So in as per the geography, this layer, the pervious strata, is followed by an impervious strata, then again a pervious strata, so that layers will be getting alternated. So that is how the earth's ground level or this crust, underneath the crust, how it is. So when people are constructing a shallow well will always be not so deep. It will be collecting the water from the first pervious strata or the first aquifer, or in rather other words we can say about
Okay, okay. I can
Is
see you
everyone
now.
over here?
Yeah,
Can you hear
yeah.
me?
Yes,
Okay.
can.
Okay, okay, okay. Thank God I prayed that doesn't go again. So are you seeing the PPT now? Or did it go? I have
Not
to
yet.
share again.
Not yet.
Okay,
Not yet.
okay, then
We see
I
you
will just share
clearly.
it again. I can share it again.
Mm.
Now?
Yes, yes. Can see, can hear.
So now let I go on the recording. Oh, it's already getting recorded. And so, okay. So, did you hear what I was saying over in this picture? What did was I lost even before that? I don't realize.
No,
Yes, yes. I saw this picture before you get lost.
but we cannot
Okay.
hear you.
But we cannot hear only. We are seeing without the audio.
Okay. So what I was saying was under the ground, when we go towards the earth crust, in our geography classes, we have learned about different layers. So as for now, we just have to remember the earth will be having different layers. Some layers there will be soil, sand, gravel, mud, clay, sandstone, limestone, so many things. So and these layers will be actually alternating. So the layers through which water will be flowing through, and also in this layer water can be collected. It is called as the pervious strata. And this pervious strata will be layer will be which will be formed with this clay, gravel and small stones, etc. Under to that pervious strata, it is called as impervious strata. So the name indicates impervious. It is not allowing something to move through it. So that's what this layer it will be made of this limestones and all very rock solids, and they are not going to allow the water to pass through it. So it is called as impervious strata. And then after to the impervious strata, we again get another layer of pervious strata where there will be water accumulation. So this pervious strata is also called as first aquifer, and the pervious strata, I mean, it is again called as second aquifer. So if we go on continue this drawing, it will be like one layer is alternating or it is followed by another. So there will be a pervious strata layer and then an impervious, then a pervious strata, then an impervious strata. So that is how the earth underneath that will be having different layers. So in case of shallow wells, the length, it is called shallow because it is not going that deep into. The length is reaching only up to the first layer, the first aquifer, the first pervious strata, just beneath the water table. And or in other words, we can say it is about to the or it is collecting the water about to the first impervious strata. So that is how we are explaining, and this I am stressing again because I have seen in many MCQs this is being asked. Where is the water in the shallow well tapping from? So it is coming from the first about to the first impervious layer, above to the first impervious layer, and then we go and see the deep well. We can see it is very long enough and it is actually tapping the water from the second pervious strata, the second aquifer, or in other words above to the second impervious strata. So that are the different expressions in which we indicate whether it is a shallow well or a deep well. If it is tapping the water above to the first impervious layer, it is called as the shallow well. And in case of deep well, the water is being tapped from above the second impervious strata. Or in other words, below the first impervious strata. Just remember this picture so that if MCQ is asked, you would be able to answer. So shallow well, it taps the water from above the first impervious layer. They yield actually limited quantities of water because the water may get dried off, and because it is very close to the human habitat or human dealings, the water is very much liable to pollution unless care is taken during its construction. But in case of deep wells, it is going so deeper and mostly machine dug. It is not easy like a shallow well to construct a like a something of a mud over there. In case of deep well, because it is going deep, we need actually something with a machine. It has to be machine dug and several hundred meters deep. It is tapping water from the water bearing stratum or the pervious strata, the second aquifer, which is below the first impervious layer. So above the first impervious layer, it is the shallow well. Below to the impervious strata, the first impervious strata, it is the deep well. The deep wells furnish the safest water and are often the most satisfactory sources of water supply. So up to all now, all the other surface waters or the any water source we have learned, we saw the rain, we saw the surface waters, the river, streams, tanks, then we saw the sea water, and then we came to the groundwater. And from what we learn is, though rainwater is the purest, it is not easy to rely on rainwater for everything, like in every season. So the best thing for a human usage, it will be the groundwater, and among the groundwater, it will be the deep well that is most satisfactory source of water supply. But the well is also not free from contamination, especially the shallow well. So what are the possible ways or different ways of water getting contaminated? So this is more obvious by the picture itself. You can start with the direct contamination. If it is kept open, there are wells which are kept open, which is not covered properly. So like that in the case of tanks, what we saw, people will be coming over here and they will be doing their ablutions, their washing, everything, and that water will be again flowing to that rivers. I mean, sorry, wells. Then there can be some waste dumped over there. Even that can be getting mixed with the underground water. Even the animals, the domestic animals, which are being brought over there to wash or to make them drink water, even their waste materials can get into the groundwater. Then what is that? Pooling of water in the cement floor. People, if especially they are sitting over there and washing the clothes or washing the dishes, uh, pool of water will be accumulated, and slowly this water can percolate and get into the water table or this under to the shallow well. Dipping bucket open to contamination. If there was water column up to this level or something, you can guess people will be like, okay, directly put their bucket and take some water. So dipping their personal bucket like that into the water, which is used by a lot of people. No fencing or adequate protection, so that people will be like, they will be like a river, they will be going very near to that. Then sometimes there may be even pit latrines. Pit latrines that we'll see in the next chapter. Actually, they don't have that septic tank concept, but it will be collected like in a tube thing and under the soil actually. So if it is very close to the water or the shallow well, even that contamination can also take place. Then other urban contaminants like oil and chemicals. So in different way, the water can get contaminated. So what are the different ways by which we can make, because we told that wells are comparatively the safest and the cheapest source of water supply, especially in a developing country like India. So what is the way that we can protect the well? So what are the things that are causing contamination? All these, if we are going to solve the problems, then we can call it as a safe well, or the term we use is sanitary well. So the word sanitary means connecting it to the word sanitation, something that is very clean, hygiene, etc. So that is the term given to a sanitary well. Now this can be asked as a short note or a 5-mark question. What should be the requirements to call a well a sanitary well? So there are so many requirements. Yeah, like 9 requirements are there. So starting with location, what should be the location of the sanitary well? So there are 4 criteria according to the location. The first step in well construction is to choose a proper site, and the best site, then this is very important for MCQ also. If to avoid bacterial contamination, the well should be located not less than 15 meter or 50 feet from likely source of contamination. So example, in this picture, when we see that there is a pit latrine near to the because we are actually saying about a well supply, a public water supply, especially in some rural villages, okay, not in a city with all the apartments. No, we are not saying about that. Some rural area. So in rural area, may not be the all the people are having a septic tank. They will be having just pit latrines. So that is a area of or a source of contamination, a bacterial contamination. So the minimum requirement, what we can do is better the which is that this one, the well should be in a higher level than to the latrines, which means the latrine should go down deeper down. But if it is not possible, at least keep a minimum distance of 15 meter or 50 feet. That should be the minimum distance between the source of contamination, the bacterial contamination, and the water source. The well should be located at a higher elevation with respect to the possible source of contamination. But when we say it should be at a higher elevation, it shouldn't become a shallow well also. It should be ideally a deep well, but which means the pit latrine should be going more deeper layer, and that is also not technically that much possible. The distance between the well and the houses of the user should also be considered, because if the people have to walk a long way to carry water, then they may not be using it. So the recommended distance of the well, that is that public well in that village, it should be that no user will have to carry water for more than 100 meter or 100 yards. So remember these two numbers. One thing, from the source of contamination, it should be 15 meter or 50 feet, that is away, and it shouldn't be like if it is a well that is supplying water to all the villages or a particular village, from each house, if we are going to see that there shouldn't be a need that they have to carry water for more than 100 meters. But this is a criteria only, okay. How much it is followed, it depends, because I know, and maybe some of you knows, there is a state which is a desert state in India, Rajasthan, and also in Gujarat. Some areas of both these states are having our Thar desert, and they actually, the people have to go or walk through kilometers, leave 100 meters. They have to walk through kilometers to bring the drinking water. That's the situation in those remote areas. So that's the criteria regarding the location. Then coming towards the lining, especially this one. Where is the picture? Over here. In case of shallow wells, if we go somewhere, I don't know whether you have seen, this can be made up of even mud actually, not a proper cement or something laid over there, but just mud. So anything can be getting percolated easily through that mud. So the second criteria is the lining. The lining of the well should be built of bricks or stones set in cement up to a depth of at least 6 meter or 20 feet, so that the water enters from the bottom and not from the sides of the well. So make that lining so deep, so strong with the cement, so that nothing can be percolating from the sides, but only entering from the bottom. So even here, even if the pit latrine is on the higher elevation, if we manage the distance between this pit latrine and the shallow well, and provided we are lining the well very well, this lining is made up of stones and cement, then the contamination is not easy, because it is not going to percolate easily through that thick cement layer. Only if it is made of some mud or clay, then it is going to easily percolate. So that is another criteria. The lining should be there. You don't have to remember this value, 6 meter and 20 feet, no, but just remember that, so that it makes sure that the water is entering from the bottom layer only, from the pervious strata, but not from the sides of the well. Then there should be a parapet wall up to a height of at least 70-75 centimeter above the ground. You can see actually the picture. So there is a strong lining, and then a parapet wall should be there to provide, so that the problem that it was open, it had seen that the open condition that will be that we can avoid, because this will avoid the people going nearby to that one, or the direct contamination, and then also the pooling of the water, and the dealing with the bucket, putting their own bucket, all these things. And also if some birds are flying, or birds coming and sitting over there, or some waste things coming from the atmosphere, nothing, it will get easily polluted. So to provide it with a parapet wall, there should be a platform like this, a platform, and this platform will make sure that the water is not getting pooled. This parapet is, the platform is advised to have a slopy area. So even if the people are doing something near, like washing and all, that water, not, they are not allowed to wash actually. If they are collecting the water, there is probability that water is going to get spilled off. And if there is a platform over there which is sloping in nature, it means the water will be flowing down. It is not going to get accumulated over there. So there should be a cement concrete platform round the well, extending at least 1 meter or 3 feet in all directions. Don't have to remember that value. The platform should have a gentle slope outwards towards a drain along its edges. So like this, a slope, a platform with a slope, so that the water will be draining off easily. The second one, there should be a drain, a pipe like something, a pakka drain, something like a cement, which is nicely built. There is a term you can see, pakka and kacha. So pakka means something that is made of cement, masonry, etc., very strong. And if it is not that strong, made of mud, clay, etc., it is called as kacha. So the drain should be the, which is pakka drain or made of cement, and the function of that will be, already we made the platform slopy in nature, but still it will be very nice if that slopy is being connected with a pipe or a drain, so that the water will be not getting accumulated, it will be just taken away from the well. So even if it is a slope and there is no drain over there, what we assume is, when the water is flowing off, it will be still collecting somewhere over here. But if there is a drain kept over there, and that drain is longer enough, taking to some distance, maybe if there is a nearby vegetation or an agricultural land is there, and if they are connecting that drain to this agricultural land, even the agricultural land will be getting benefited, that water can be gone. But make sure that the people are not using it for domestic purpose, only they, when they carry the water or they fetch the water, only those water is getting accumulated over there, not by their personal usage. So it is ideal to have a drain actually to carry off spilled water to the public drain. There should be a covering. The top of the well should be closed by a cement concrete cover, because the bulk of the pollution is introduced into the well directly through the open top, people throwing things away. Then there should be a hand pump or some other method like a bucket or somehow that the people can take water from, because it is deep, uh, wells, so the water depth will be so deeper. We need some kind of help, a hand pump and a sanitary bucket also, which is actually kept as a public thing. It is not that you bring bucket from your own house. Sometimes we feel that is more safe, more sanitized, but it depends on the people who are using it. Like some people may be keeping everything in their house very sanitized, so yeah, they may be like how to use it in a public thing, because not all the houses will be having that hygienic practices. So it will be very ideal that they have a public pail or a bucket to fetch the water also, and people ideally keep that bucket cleaner. Then consumer responsibility, all those personal ablutions, washing of clothes, dumping of refuse, waste, etc. nearby to the river should be prohibited. And the quality of water should also be enough. What are those qualities will be coming and seeing in the next few slides. So the physical, the chemical, the bacteriological quality of water should be conforming to the acceptable standards of quality. Then only it will be called as the sanitary well. So 9 criteria, first one regarding the location, then a parapet wall, the lining, a platform, drain, covering for the well, a hand pump, and consumer responsibility. And after to that, finally, what is the quality of the water that is coming, and whether it is within the accepted level, the physical, chemical, and bacteriological quality. That's also important. So this is another picture of the shallow well and the deep well. You can see how it can get contaminated, especially the shallow well. So ideally to keep that distance, that's what they mean. And also the lining also to be very strong, that's what they mean. Then the last source of the groundwater is actually springs. So when groundwater comes to the surface and flows freely under natural pressure, it is called as a spring. The mineral springs, many of our medicines we have from the mineral springs, you know that its opening will be there and the water is actually coming out from the ground actually. So springs may be of two types, shallow springs and deep springs. In case like that of the shallow well, the shallow springs, similarly, they also can dry up quickly, especially during summer months. Whereas in case of deep springs, we don't see such fluctuations in the flow of water. However, it is exposed to contamination and it is easier for people to exploit because no pumping is needed to bring the water to the surface. And there are water companies, I don't know, who just market this spring water, saying that it has got, yeah, because the minerals are present, it is coming deeper from the ground, so it is having some minerals in it, and that is why we also use it as our medicine. But there are companies which market this and making profit by this. So the springs are easier to get exploited. Well-built protective structures are necessary to safeguard the water quality. So regarding the water sources, the question that can come over there is what are the different sources of water, and then I may choose one of it and then ask you to explain the characteristic advantages and disadvantages of that particular water. That's one way of asking the question from that portion. So now we go towards water pollution. So water pollution, it can happen via two methods, that is natural and man-made. So in case of natural impurities or natural pollution, it is not essentially dangerous. What it can maximum make is the water taste may be changing, color, appearance may change, but that is not going to make someone very sick and all. So natural impurities are not essentially dangerous. It may be dissolved gases like nitrogen, carbon dioxide, hydrogen sulfide, which may be picked up during rainfall. And if it is hydrogen sulfide, it is a bit dangerous. Not that the person will be killed immediately. That might be the saying it is not essentially dangerous. Or it can be the dissolved minerals, the calcium, magnesium, sodium, etc. Its minerals, making it hard in taste. Um, and also it can be suspended impurities. in that water naturally, the clay, silt, sand, mud, etc., and also microscopic organisms, because they have their habit in the under the ground or the earth layer. So even that will be the, so these four things, the gases, the dissolved minerals, suspended impurities, microscopic organism, these are actually the natural impurities seen in the water, but not essentially dangerous. But the dangerous water pollution, what we mean is that what is being created by ourselves, that is the by human made or by human activity, especially by the process like the urbanization and also industrialization. So the sources of pollution resulting from these are sewage. It contains the organic matter. I told you it is the domestic water which will contain the fecal matter also. So mixing of the sewage into the water body, that can result in a water pollution. All the industrial and trade waste, I told you in the last class itself, there are possibilities. It is actually advised that the waste pipe from this industries should be actually moving, it will should be kept into the sea something after treatment. But some medium class or moderate class industries, they may be connecting their pipes to drain the wastewater directly to some rivers or something or streams because of its low cost. So the industrial and trade waste which contain toxic agents ranging from metal salts to complex synthetic organic chemicals, depends upon what the industries are dealing with, that can get mixed into the water. It can be agricultural pollutants, especially when fertilizers, pesticides are used, that may also wash off, and it can bring about pollution. The physical pollutants, example the heat, the thermal pollution, and also the radioactive substances. So these are the man-made pollution, and this is essentially dangerous. So how we know whether the water is polluted or not? Sometimes yes, by seeing itself we may understand, but sometimes it may be due to the smell. We have a very characteristic smell or something, or sometimes it may be some oil suspension that we see, or some taste difference we can understand. But if we are going to say it in a technical manner that the water is being polluted, how we can say? The amount of total suspended solids, the biochemical oxygen demand at 20 degrees Celsius. The third one is concentration of chlorides, nitrogen, phosphorus, and absence of dissolved oxygen. So among these three, the indicators of pollution, the most important will be the second one, BOD, or the biochemical oxygen demand at 20 degrees Celsius. The other one, the suspended solids and all, they may be keeping the water in the, the water labs other will be keeping it for some time so that it gets sedimented, and then they may be using some chemical reactions to understand what are the solids, and in maybe they also do the quantitative analysis to calculate how much quantity of such and such minerals or solids are present inside that water sample, even in the same case with the chemicals. But for us, the most important to remember over here will be this one, the BOD, or the biochemical oxygen demand at 20 degrees Celsius. So what this means, there is a big definition that is given. So it provides a measure, the BOD, or biochemical oxygen demand, it provides a measure of the impact of waste on the oxygen content in the receiving water body. Wastes are broken down by microbial organisms who require oxygen for this monumental effort. So what this sentence is saying is, in the water, actually there will be some microbial organisms also, the aerobic bacteria, and they are very capable of removing the waste material. What they do is they will be, because of their action, the aerobic bacteria, they will use oxygen, and they are going to use the oxygen that is present in the water, and using that oxygen they are going to break down the waste that is getting mixed up with the water. So in BOD, it is actually measuring how much oxygen will be used by this bacteria to break down that particular waste. So it provides a measure of the impact of waste on the oxygen in a receiving water body. So suppose that's the definition given, but change it in our own words. Uh, it is the impact, how much uh, worse or better than, not better anyway, how much worse the waste that is getting mixed with that water body. Water body, maybe we can consider it as like a river or a stream. How much impact it is going to bring about the waste on what? The oxygen content. And why oxygen content? Because the oxygen content will be used by the microbial organisms to break down this waste. So the waste you are adding into, or not you, the industries are adding into a river or sea or whatever, that is going to be broken down by the microbial organisms. And because they are aerobic, they will do this process utilizing the oxygen. So if the BOD is actually very high, it shows the water quality is very low. So if at 20 degrees Celsius, if a group of bacteria, the aerobic bacteria, are able to break down the waste, but they are using a lot more oxygen than the waste that is being accumulated in that water is of high grade, and the pollution is also very high. So the biochemical oxygen demand will be very high, which indicates water quality is very less. So for example, if I say BOD is 50, suppose the BOD I'm saying is 50, which means uh, the waste that has got accumulated in that water body, it had got that much waste, organic waste, and that is why 50 percentage of oxygen had to be utilized by these bacteria to break down that waste. So which means in other, the oxygen quantity in that water is very much reduced. That indicates pollution. But if I say BOD in a particular river is 10 or 5 or even 1, it indicates that water is of high good quality, because no much pollution has taken place, because the oxygen level is being retained over there. If it is only BOD, that is 1, which means 99 percentage of oxygen is still remaining in the water, which means the aerobic bacteria didn't have to break down much waste, which means the pollution is very less. So that is how we connect biochemical oxygen demand to the pollution. So we have 3 indicators of pollution. I'm just repeating it. And the most important one is biochemical oxygen demand, or BOD. And why it is important is the organisms, the bacteria, the aerobic bacteria present in the water body, be it river, stream, anything, they do have the ability to break down the waste material. So when a waste is coming, which is requiring the bacteria to use much of their energy, which means they will be utilizing maximum quantity of oxygen from the water to break down this waste, then BOD of that water will be high, because they are using a lot of oxygen. The oxygen demand by the bacteria at 20 degrees Celsius is very high, which means the oxygen that is remaining in that water body is very less. It shows that it is highly polluted. But if the BOD is very less, it means no much waste has been accumulated in this water body. That is why the bacteria didn't have to use much oxygen from the water to do this waste breaking up. And this water, when we say BOD is only 1 or 2, it means that water is of high quality, or the pollution is very, very less. So that is the importance of BOD. I hope you got the concept of BOD. Did you, or should I repeat again?
Yeah, okay.
Okay. So seeing the indicators of pollution or BOD, maybe asked as a short question or a MCQ somehow. So purification of water, we go towards the seeing the sources, the different um, uses. Now we are going towards the pollution. Now how to do its purification. So it can be considered under two headings: the purification of water that is done in a large scale, and the purification of water done in a small scale, like in a household level. The other one is large scale. If the water is being supplied, like in cities or municipalities, if it is supplied in a larger quantity, how it is being done. The purpose of water treatment is to make it safe and wholesome. The method of treatment to be employed depends upon the nature of that raw water, from where that raw water is coming, and the desired standards of water quality. For example, if it is groundwater, like wells and springs, as we told earlier, it may not need any particular treatment, only the disinfection is required. But if it is surface water, rivers and streams, we saw that it may be extremely contaminated, it may be turbid, polluted, it requires extensive treatment. So it depends upon what water you are using, the source of that water, how much purification has to be done. The components of a typical water purification system comprise one or more of the following measures. So there will be a storage, initial storage, then there will be a filtration mechanism, and then there will be the process of disinfection. So this is the basic purification system steps. Initially a storage, then the filtration, the third one is disinfection. So in case of groundwater, they may not need the storage and filtration, they require only the third process, the disinfection. But in case of surface water, obviously this water have to go through all these steps. So the first process, starting with the purification, the first process, that is storage. So when we were learning the impounding reservoirs or the dams, we have seen that water, if it is stored for some time, like for less than 14 days, it is ideal because it will allow the suspended impurities to get settled down. So storage for a considerably shorter time is okay, but not at all okay if it is for a larger time, then it will result in the growth of some aquatic plants. So when we are saying about the river water, if you remember, we told that some kind of self purification is happening in case of river water, because there is a pooling of water. The river water is continuously flowing, but sometime if there is a pooling of water in some area, it is a kind of storage. The water is getting stagnant for some time, not for a longer time. That time there is a chance that it become clear. The suspended impurities may get settled down, so that we get the clear water. So as a result of storage, a very considerable amount of purification take place. This is natural purification, and we may look at it from 3 points of view. The first one is physical. What I told you now, by mere storage, the quality of water improves. About 90% of the suspended impurities settle down in 24 hours by gravity. The water become clearer. If it is a turbid water, we can keep it for some time and then it will be getting settled, you know that. And then the water will become clearer. This allow penetration of light and reduces the work of filter. So the filtration process, that heavy work, that filter have to be done, it will be done by the light because it's a natural disinfectant. The second is happening chemically. Certain chemical changes also take place during storage. The aerobic bacteria oxidize the organic matter present in the water with the aid of dissolved oxygen. What I told you in the previous slide. The aerobic bacteria will be, there are bacteria actually, and it is beneficial also. And this bacteria will be breaking down the waste materials. So when we see, I mean, go through the next chapter, when we see how to dispose the waste, sewerage tank, etc., we'll see that ultimately after the treatment, the waste materials are disposed in sea actually, because there are a lot of microorganisms and they will be breaking down this organic waste. But when they do that, we should make sure that the sewage or the industrial waste is not coming directly from the industries. Some kind of treatment should be done, and then that comparatively safer waste materials, which is free of pathogenic organism, and which won't be using much of the oxygen content from the sea, only that should be disposed over the, not the pre-treated one. So there is, because these organisms are present in the water body, the waste material that is reaching the organic water matter, that waste matter, that will be broken down. As a result, the content of free ammonia is reduced and a rise in nitrates occurs. So for example, if it is a sewage or a sullage that is coming from agricultural lands, because agricultural land, they use fertilizers which is rich in nitrogen, which means ammonia may be there. So when this storage is taking place, the bacteria will be breaking down this ammonia, and then it will be changed into comparatively not so problem or innocuous nitrates. So even this chemical change is happening during the process of storage. The third process that is happening is biological. And biologically, which means some microorganisms are getting died. So this happens, the pathogenic organisms gradually die out during storage. It is found that when river water is stored, the total bacteria count drops as much as 90% in the first 5 to 7 days. This is one of the greatest benefits of storage. So when we are storing water, there are physical, chemical and biological purification happening some or the other way in the water. But the optimum period of storage of river water is considered to be about 10 to 14 days. If it is stored for longer periods, there is likelihood of development of vegetable growth such as algae, which impart a bad smell and color to water. So that is the benefit of the storage, the first process in purification. The second process is filtration. Now this is important, the second stage. So filtration is the second stage in the purification of water, and quite an important stage because 98 to 99% of bacteria are removed by filtration. So one of the most important thing from the water is it should be free of the pathogenic organisms. We do have chemicals, it is going to bring about danger, yes, but the most or the immediate danger will be because of the presence of pathogenic organisms, be it parasites or cholera, that bacteria. So they are going to bring about diarrhea, dysentery and all other diseases. So the most essential will be the removal of these pathogenic organisms, and 98 to 99% of that it happens during the process of filtration, the second one. Two types of filters are in use, the biological or slow sand filters and the rapid sand or mechanical filters. So we have slow sand filtration and rapid sand filtration. The slow sand filters are also called as biological filters. There is a reason why we call so. And then rapid sand filters are also called as mechanical filters. Now starting with the slow sand or biological filters, this slow sand filtration or rapid sand filtration can be asked as a short note. So the slow sand or biological filters, this was first used for water treatment in 1804 in Scotland, and later to that it was used in London. During the 19th century, their use spread throughout the world. Even today, they are generally accepted as the standard method of water purification. Elements of a slow sand filter, there should be some supernatant or raw water, a bed of graded sand, an under drainage system and a system of filter control valves. So this will be a slow sand filter in diagram. This will be in use, okay, the larger sized or a bigger size one. So what we now see is actually the water only. Underneath there is a filtration mechanism that is going on. So what that filtration mechanism is, the diagram is over here. So we have superficially a supernatant, so superficial layer of water, the raw water, which is not being treated, that is what. So there will be an inlet pipe through which the raw water enters. Then there is a layer which we call as a biological layer, or I don't know how to pronounce this, Schmutzdeck. I will continue pronouncing like that. Mostly it is a German word, I think. I guess so. It is a German word. It means it is actually a layer of algae, plankton, etc. And this layer is very important because this is the layer, the algae, planktons, etc., which is going to remove the bacteria, microorganisms from the water during this process of filtration. So in slow sand filter, they are going to use this biological layer, the Schumsdeck layer, and that is the importance of slow sand filter. And such a layer, biological layer, we don't find in rapid sand filter, and that's why that one is called as a mechanical filter. And because this is a biological layer made of plankton and algae, this slow sand filter is also called as a biological filter. Then after to that, there will be having sand of different sizes. Then there will be gravel, that also the size will change, and then an under drainage pipe. So we have a supernatant water layer about 1 to 1.5 meter, and that will be always kept constant so that the pressure is always maintained. Then there is a Schmutzdeck layer, the black one, the biological layer I told. Then a sand filter, the principle that what we learned in the groundwater itself, because the sand, the clay, the gravel, etc. So the water that is coming out will be getting filtered. So there is a sand filter, and that can be anything varying from 0.6 to 1.4 meter depth, and then a gravel layer, and then under drainage. So we have another picture. You can see the sand. Even the level, size of the sand is changing in different layers. So there is a very small filter sand, then a little more bigger, the coarse sand, then the fine gravel and the coarse gravel. So the water, when it is coming from the supernatant layer, it is going through different layers, and then when it passes through in different layers, some of the impurities, the suspended materials, the bacteria, everything is getting filtered in different layers, and then finally the water that is coming out from the under drainage system, that will be very efficient. So here also you can see the different sizes of the gravel that is being used, the under drainage. So now we'll go to the details. So we saw that there is a supernatant layer of water which is about 1 to 1.5 meter, and it is of two purposes. One is to provide a constant head of water or a constant consistency or a pressure that is being kept constant over the. Secondly, that is also a kind of storage, a waiting period of some hours, 3 to 12 hours, depending for the raw water to undergo partial purification. So what we told, the storage, it is happening again in the process of filtration also. Water will be kept constant over there for 3 to 12 hours, so that some, because of that constant standing, some sedimentation also will take place, and there is a partial purification. Then after to the supernatant layer, we have the sand bed, which is the most important part of the filter. The thickness is about 1 meter, and you have to remember this one. Actually, whatever number that I have put in color, you have to remember. It may be Oxford MCQ. So the sand grains that has been used, it should be preferably rounded and have a effective diameter between 0.2 and 0.3 millimeter. So that should be the size of the grains that has been used. And now if you are thinking why you are studying these things, because there is another important thing, what is the difference between rapid sand and the slow sand. And in both the things, one difference we already told, the absence of that Schumach layer in case of rapid sand. Another one is there is difference in this size of the gravel that is being used in the rapid sand filter. So that is why you have to remember what is this, the sand size that is being used in the slow sand, the 0.2 to 0.3 millimeter. The sand bed is supported by a layer of graded gravel 30 to 40 centimeter, which also prevents the fine grain being carried into drainage pipes. So this will be a larger size one. So if the water is coming out, the smaller sand, they have a tendency to come down and then get filtered. But because of the presence of this gravel, it will be that sand will be collected somewhere over there and it won't be getting into the drainage pipes. So that is with the sand bed. Uh, this actually to see this only I thought of going to the water purification, etc. In fact, I contacted the India Water Consortium, right? India Water Consortium last week. I emailed to them. I'm waiting to hear, but I don't know where, because it is a government institution. Will they allow us? I don't know. I'll just see. Anyway, when we go there, we see this underneath the process, it is happening like that. So the sand bed, it presents vast surface area, some 15,000 square meters of surface area. As seen in this picture, it is actually that much, the filtration, the sand layer will be of larger surface meter, which means the water will be slowly percolating and every kind of purification or filtration happens when it passes through that much big square meter area. So the water percolate through the sand bed very slowly, a process taking 2 hours or more, and when it does so, it again undergo purification. The straining, like a filter medium, it is coming out like a sieve, it is acting, the sand is acting. So mechanical straining, sedimentation, adsorption, oxidation, bacterial action, everything is playing a part when the water is flowing through this sand layer in such a slow speed. The design rate of filtration in case of a slow sand filter, this number also you have to study, it is between 0.1 and 0.4 meter cube per hour per square meter of sand bed surface. That is the speed of water, like the filtered water that will be coming out from the slow sand will be in such a range. Then we have the vital layer, the biological layer, which is the most important one. So when the filter, the slow sand filter is newly laid, it acts merely like a mechanical strainer and cannot be considered as truly biological. But very soon, the surface of the sand bed gets covered with a slimy growth. That's called as the Schumstack, or vital layer, or zooglial layer, or biological layer. And this layer is slimy, gelatinous, and it contains thread-like algae, plankton, diatoms, and bacteria. And once this layer is formed, it is actually called as the formation of vital layer is called as the ripening of the filter. Can be asked for a MCQ. The vital layer, or this biological layer, or the Schumann's layer, is also called as the heart of the slow sand filter. Unless this Schumann's layer is not formed in a slow sand filter, it can't be called as a slow sand filter. In fact, when in some water treatment area, they have laid down this slow sand filter, and then they started passing the water through it, and as they say, it will take some days, 1 week or 10 days, for this layer, biological layer, to form. And until that layer is formed, the water that is draining out, it is not used. They are actually, you can see the first few days filtrate is usually run to waste. They won't use it. Only once they make sure that that zooglial layer is formed, or that biological layer is formed, then only they consider that the slow sand filter is ready to use, or it has got ripened, and then they will be using that water for drinking or whatever be the purpose. So this layer, it removes the organic matter, holds back the bacteria, or it is removing the bacteria, oxidizes ammoniacal nitrogen into nitrates, and help in yielding a bacteria free water. So that is the benefits of this sand layer and also the Schumann's layer. Then under drainage system, two purposes are there. One is to carry the water outside, outlet for the filtered water, and also another is acting like a support for the layer over. that there is supernatant water, there is sandbed, that the gravel is the so underlying drainage or that pipe, they will act one way to take that filtered water away, and also second one to provide a support. Then there will be a valve mechanism of filter control, and the purpose of this device is to maintain a constant rate of filtration, which we already saw that it is between 0.1 and 0.4 meter cube per hour per square meter. So this is center one, where we have the supernatant water, the Schumann's layer, the sandbed, the gravel layer, the under water drainage system, a control valve, and then the water being collected. And now this water is ready to be used. Not ready to be used, it will again go to the process of disinfection, because we have done only the second process now, the filtration. Now how to clean this slow sand filter? Normally it will run weeks or months without cleaning. When the resistance is increasing, bed resistance that is increasing, it will lead to the opening of the valve, and then we understand that it is the time to clean. The supernatant, and during cleaning the supernatant water is drained off. The sand layer that is being scraped for 1 to 2 centimeter, and it is done by unskilled laborers. After such 20-30 scrapings, the sand bed, its size will be decreasing, because the superficial layer they are going to scrape off like 1 to 2 centimeter. So after, when they do it for 20 to 30 times, the superficial layer, that the sand layer, it will be scraped to 0.5 to 0.8 meter. At that time it is time to close the plant. That is how the thing is being done. And why you need to learn, because obviously, as I told earlier, in rapid sand filter, all of this is going to be very different. The advantages of slow sand filter: it is simple to construct and operate. The cost of construction is cheaper than that of the rapid sand filter. The physical, chemical and bacteriological quality of filtered water is very high, and if it is working ideally, it is seen that the total bacteria in that water reduced from 99.9 to 99.99 percentage. Sorry, it did not reduce from, it will be reduced up to this level, 99.9 to 99.99 percentage, any other bacteria. And if it is E. coli, it will be reduced to 99 or to 99.9 percentage. So that from that values itself you understand the importance of slow sand filter, and how much effective it is to filter out a safe and wholesome water, which is having very less pathogenic organisms. It is simple and also very much cheaper. But when we go towards rapid sand, we'll see it is highly costly to make it, and it has to be, the maintenance is difficult. Maintenance difficult. Maintenance difficult is here, I guess. Then another feature of slow sand filter is this will require a lot of area. You already saw in the picture. It requires a lot of area, but in case of rapid sand, it doesn't require much area. So now going towards rapid sand or mechanical filter. This was constructed in 1885, slow sand in 1804 in Scotland. But in 1885, years later, the first rapid sand filter were installed in the USA. Since that time, they have gained considerable popularity, especially in highly industrialized countries, because it is very costly to make it. So it's only the industrialized country they tend to do the rapid sand. However, we can never say that just because rapid sand is very costlier or expensive to make, it provides the safest water. We cannot say like that. The safest water is actually coming from the slow sand filter. But the only problem is it requires a lot of area. And this one, it doesn't take much area. And also, so in those countries where there is much people living in congestion, and they don't have that much space to build a slow sand filter or filtration things, then they go for the rapid sand. So rapid sand filters are of two types, the gravity type, the Patterson filter, and the pressure type or the Candice filter. Both the types are in use even now. The following steps are involved in the purification of water by rapid sand filter. First one, there will be coagulation, then a rapid mixing, flocculation, sedimentation, and filtration. So when we were learning about the slow sand filter, we saw that the water is going to be stored for some time as a supernatant water. Then via the biological layer or the different sizes of sand and the gravel, it is slowly getting filtered out. That is what happening in a slow sand filter. But in rapid sand filter, that water that is being coming, it is actually treated. It is actually treated with alum, so that there is by the process of coagulation. Now this steps what we are saying going to say now, this we have not seen in slow sand filter. In slow sand filter it was just storing the water for few hours and then allowing it to pass through. We didn't do any pre-treatment to the water. But over here in rapid sand they are going to pre-treat the water. So for the first one will be coagulation. The raw water is first treated with alum. The dose can vary 5 to 40 milligram per liter. You don't have to remember this value. And this value will change depending upon the turbidity, color, temperature and pH of the water. So anyway, the first process is mixing the water with the alum. The second one is, initially only the alum will be added according to the quantity that happens in a coagulation chamber. And then it goes to the second one, that is rapid mixing. There is a violent agitation is happening over there in a mixing chamber for few minutes. This allows that water and the alum to get thoroughly mixed. The quick and thorough dissemination of alum through the bulk of water, which is very necessary. Then there is a flocculation. Now there is a gentle and slow stirring of the treated water in a flocculation chamber for about 30 minutes. Then it is allowed to sediment. The coagulated water is now led into sedimentation tanks, and here it is detained for 2 to 6 hours, so that all this when the alum was mixed, obviously it is going to get mixed with the suspended impurities, organisms, etc. So that suspended things will be getting settled down in the tank, and only that water is carried or subjected to the rapid sand filtration. So in case of slow sand, no such pre-treatment happened. It was just allowed to store for a longer time and then allowed to pass through the sand layer slowly percolating. But over here, because it is that is why it is called as rapid also. It is done so soon. So initially the water is mixed with some alum, then it is rapidly mixed, then it is allowed to get gently stirred and allowed to sediment for a longer time, around 6 hours, so that the suspended impurities get settled down. And then it is ready to go through the second process, that is the filtration. So this will be the flow chart for case of rapid sand filtration. You see the water is coming from river. So for the slow sand, of course, the groundwater, etc., can be done because there is no pre-treatment that is done. But if it is river water, which is very polluted, contaminated, turbid, we have to mix it with alum, then the mixing chamber, the flocculation chamber, then allowed it to settle in the sedimentation tanks, and then it passes through the filter layer. A chlorine is also added over here, and then water is ready for the consumption. Now going towards the filter bed, what is happening over there is each unit of filter bed has a surface of about 80 to 90 meters square, doesn't matter, but this one, the effective size of the sand particle, it is little more bigger. Over there it was 0.2 to 0.3, right? What was the size in sand? 0.2 and 0.3 millimeter, that was the size, and over here it is 0.4 to 0.7. 0.4 to 0.7 millimeter. The depth is usually about 1 meter. That was the same in case of slow sand also, 1 to 1.5. Below the sandbed layer is a graded gravel level 36 to 40. I think in slow sand it is around 70. The depth on the water, it is 1 to 1.5 meters, same to that of slow sand. The rate of filtration. And the next value that you have to remember is the rate of filtration. Over there it was very less, 0.1 to 0.4 something. But here it is coming out rapidly, 5 to 15 meter cube per meter squared per hour. So advantages, rapid sand filter can deal with the raw water directly because it is getting treated. There is no need of preliminary storage as like we saw in slow sand filter. The filter beds require less space. Filtration is very rapid, 40 to 50 times more faster than that of a slow sand filter. And this cleaning of the filter is very easy. So this will be the difference between rapid sand and slow sand filter. The things that I have put in brown color, you have to study that because it may be asked as a question. So in rapid sand filter, as we saw, there will be process of coagulation with alum, flocculation, sedimentation we are doing. But in slow sand, no pre-treatment is required, just storage. Then effective size of filter is 0.4 to 0.7 mm. Over here it is 0.2 to 0.3 mm. Then in rapid sand filter, size of filter unit, you don't have to learn that. Leave this sentence. The rate of filtration, that is important to learn, but here they have changed the unit. So don't bother about it. What I have put in the previous ones, per meter cube, per meter square, study only that one. Then the cost of installation in case of rapid sand, it is less, but the operation cost is more. Oh, okay. And over here, the cost of installation is high, but operation cost is less. The maintenance is less. It has an efficiency of removal of bacteria 80 to 90 percentage. And in case of slow sand filter, it is about 90 to 99 percentage. So you understand the difference. So even when we say rapid sand filter was introduced first in USA and it is very expensive, we tend to believe, okay, then it will be more efficient. That's why I told you it is never more efficient. It is the slow sand filter which is more efficient because 90 to 99 percentage of bacteria will be removed from the slow sand filter only. Then rapid sand filter, what to do by cleaning is backwashing. So we allow the water to stop somewhere and then it is allowed to go in a reverse manner and then do the cleaning. A backwashing is done. But in case of slow sand filter, we saw that it will be dried off and then using the scraping method, the sand bed is scraped and to some length, to some depth. Method of cleaning involves scraping the top layer of the shumats, and cleaning interval in case of rapid sand filter is 1 to 2 days, and whereas in slow sand it will be once in 3 to 4 months. Now having seen the storage, then we saw the filtration process. We saw the difference of slow sand filtration and rapid sand filtration. We are going to the third process, disinfection. So now you remember in case of this organon or PSM, you have learned disinfection separately, the different types of disinfectant. Then you learn disinfection in relation to insects, and now you are learning disinfection to be done in case of water. So, for a chemical or an agent to be potentially useful as a disinfectant in water supplies, it has to satisfy the following criteria. Of course, the disinfection that we are using on the surface, like the phenyl and all, we can't use it in water. So, the ideal disinfectant and the criteria we learned in the earlier chapters, it's not applicable over here because water is something that we are going to drink and not to be applied like the other chapter, it is not to be applied on the surface. So when we call a disinfectant which is safe to be used in drinking water, the feature changes. So to call it a disinfectant, the basic one, it should be capable of destroying the pathogenic organisms, because we saw by the process of filtration itself 90 to 99 percentage or 80 to 90 percentage is being removed, but still there is remaining, right? Still there is remaining. So we do the process of disinfection. So that chemical should be able to destroy the pathogenic organism, not necessarily chemical, it could be anything. Should not leave products of reaction which render the water toxic or impart color or otherwise make it unpotable. Nothing it should do, just treat and kill the organisms or do its function, but not making it toxic or changing its taste or smell. This disinfectant, it should be readily and dependable in availability. It should be easily available at a reasonable cost, and when we are applying it to water, it should be very convenient for us and safe also. It should have some property of leaving residual concentration to deal with small possible recontamination. A little should be there, but make sure that whatever residual activity is there, it is not affecting the health of the people who are consuming it. But there should be, like when we say boiling water, and boiling is something that we do in a household purification, and that's the best method also in a small scale housing purification. But it is told that when we do boiling, at that time the organisms are killed and all. Rolling boiling we do, it is going to kill all the organisms. But then it will change. I don't know, have you realized it will change the taste of the water. The cold water and the warm water, especially the warm water, when it becomes cold, the taste is a bit altered. Only sensitive tongues may be not sensitive, but you can understand there is a variation in taste. And but see, you boil the water in the morning, and you didn't touch that water, but at night or evening you are going to take it, there is no guarantee that there are no pathogenic organisms in that water now, because one of the most disadvantage of the boiling process is that there is no residual action. It is boiled at that time, every organism get killed, but then it is being, that pot may be opened again and again. uh, the glasses will be put or somehow the other containers to take the water out. That time there is a possible contamination, but we are not boiling it again, so by evening we can't say that the water will be safe to use. So that is why a little residual activity should be there, but it shouldn't, whatever be the activity, it shouldn't make the water toxic or impart any color or make it unpotable. And it should be amenable to detection by practical, rapid and simple analytical techniques to test the efficiency. What we mean by this sentence is, suppose the best method to disinfect water is actually chlorination. We use the chlorine powder or bleaching powder. That's how we are going to disinfect water. That is the most easiest method actually. So when we are using chlorine and disinfecting the water, then after to that we should do some, I mean we should be able to do some chemical reactions, so some test by which we know that okay, chlorine is still present over there and in how much quantity, whether this is going to cause any change of taste or smell in case of water, and whether this is enough for the organisms to get killed. Some tests should be the, by which we can detect the presence of the chemical we use for disinfecting water. So, so that it get to know whether it is efficient, that disinfectant that we use for this purpose, whether it is efficient or not, we'll get to know. In one of the later slides, you will see water can be purified even using UV rays. UV rays, and nowadays that is also a trend to purify water using UV rays or ionization method. It is costly, but only problem is this one, the fifth method. We can't do it in case of UV rays. It also doesn't leave any residual quality. So we can't say after few hours that water is safe to use, and even after UV treated, we can't do any test to know whether the UV rays have killed the organisms or whether it is present or not, how much quantity it is present, the UV rays are present. To know whether it is efficient or not, it is not possible in case of UV rays. So these are the five criteria, five only right here, five criteria to call a disinfectant for water. So the best method, the cheapest, is one of the for water purification is chlorination itself. It is actually a supplement, not a substitute to sand filtration. So the once the water had gone through the sand filtration, whether it's slow sand or be rapid sand, after that only we do this process of chlorination. It is not that we are doing chlorination, there is no need of slow sand filtration, nothing like that. We have to do the filtration and then the disinfection. And this process, what we are saying now, is actually purification of water in a large scale when it is being supplied to a whole city, municipality, etc. Chlorine kills pathogenic bacteria, but it has no effect on spores and certain viruses. Example, poliovirus, viral hepatitis, etc., except in high doses. Apart from killing this bacteria, the germicidal effect, it also has got some secondary properties. It oxidizes iron, manganese and hydrogen sulfide. It destroys some taste and odor producing constituents. It controls algae and slime organisms and aids in coagulation. So chlorine is not just removing the pathogenic bacteria, but it also does chemically all these things. Now, what is happening when we are mixing chlorine with water? So water H2O is mixed with chlorine. What we are going to get is HCl plus HOCl. HCl is hydrochloric acid. Yeah, hydrochloric acid, and then a part and majority of it will be converted into HOCl, which is hypochlorous acid, which is very weak in nature, not as strong as hydrochloric acid. And this hypochlorous acid will be again breaking down to H and or hydrogen ion and OCl minus, which is hypochlorite ions. So this is the chemical reaction happening. Why we are learning this is the disinfection action of chlorine is mainly due to this hypochlorous acid or HOCl, and to a small extent only the hypochlorite ions. So if we are going to quantify, we could say that the hypochlorous acid or HOCl is 70 to 80 times more effective than the hypochlorite ion. So this is a MCQ that can be asked in case of chlorination, which is more effective in disinfecting water, whether it is the hypochlorite ion or the hypochlorous acid. So it is the hypochlorous acid. And then this sentence is also important, the coming up one. The chlorine is acting as the best disinfectant when the pH of the water is around the neutral, that is around 7. Then it will be acting very efficiently, the chlorination. If the pH value exceeds 8.5 or if the water is highly alkaline, then we shouldn't go for the chlorination method. Or even if we do, we can do it, but what happens is in this pH, when the reaction takes place, water and chlorine is mixed and the water is of the pH of 8.5, most of the hypochlorous acid that is formed, 90%, it will be getting converted to hypochlorite ion. So we already saw that hypochlorite ions are good in disinfection water, but it is not efficient. It is the hypochlorous acid 70 to 80 times, not 6 or 7 times, but 70 to 80 times highly efficient than hypochlorite. But this reaction that most of the hypochlorous acid will be formed only if the water is around 7 pH or neutral. If the water is much more alkaline or 8.5, then hypochlorous acid that is formed, that will be most of it will be converted to hypochlorite ion, which is not efficient or effective in disinfecting water. So ideally when we do the chlorination, we shouldn't simply blind our eyes, because we already saw that it is the best method of disinfecting water, but we shouldn't blindly go and put chlorine content in any water body. There is a calculation that have to be made, how much quantity has to be mixed. But before to that, a prerequisite will be to know what is the pH level of that water. If pH level is alkaline 8.5 plus, then better don't go for chlorination. It won't be effective because the hypochlorous acid will be converted into hypochlorite ion, and that is not effective in chlorinating or disinfecting water. Then other agents other than chlorination, we can go for the process of ozonation. Then some membrane processes are there, where the membranes, different size membranes are used. So we have reverse osmosis, ultrafiltration, microfiltration, and nanofiltration. Most common application of reverse osmosis is when we have to do the disinfection or the desalination of seawater or brackish water. That's where the reverse osmosis is used. And other filtration, ultra, micro, nano, I didn't go for the detail for that. But just the differences, it's the same filtration process, but the size of the pores that is used at different levels, it changes. So in case of nanofiltration, the membrane pore size will be 0.001 to 0.01 micrometer. Ultrafiltration 0.002 to 0.03 micrometer, and micro, the pore size will be 0.01 to 12 micrometer. You don't have to study this, but understand other than chlorination, there are methods of ozonation. But as I told, ozonation, we don't have any test to check for the presence of ozone later. And also it is very expensive, and also there is no residual action left. Then we have the membrane processes, including reverse osmosis, which is used for desalination of the seawater. Then ultrafiltration, microfiltration, and nanofiltration. And the changes or the differences are based on the pore size that is used in the sea, and that size varies. So having done with the purification of water in small and large scale, that is the storage, the filtration, the disinfection, see how to purify the water on a small scale. I finished 3 or 4, this one also. So water in a small scale purification means the household purification. The best one is boiling, or commonly done in all the house one. Can't say the best one because of the problem I told. But it is the most common thing that is being done in every household. Then we can do chemical disinfection. The bleaching powder can be used. Chlorine solution may be prepared from the bleaching powder. There is actually a ratio that is to be used, a concentration that is to be used, like every 1 liter of water, such milligram of the chlorine have to be used. That's the formula to be carried out, and find out the quantity that is required, and then put it in the like purification of water in household means, in some villages, especially about the Indian level, we will be having wells. So if there is the need to disinfect in the well, then it's not, we are just simply putting 1 kilo bleaching powder. We have to calculate and do. So I didn't put that values and all. I need to by heart all those numbers. But that is the basic principle. There is a quantity of chlorine or the bleaching powder that has to be calculated and found out according to the water level in the well, etc. Then high test hypochlorite, or HTH, or perchloron, which is a calcium compound, and it contains 60 to 70% available chlorine. It is more stable than bleaching powder, and it deteriorates much less on storage. Bleaching powder, you may be knowing, if you are going to keep it for a long time, the chlorine is going to get deteriorated. It is very unstable actually. But hypochlorite, we can keep it for a longer time. Chlorine, or bleaching powder, we can't keep it for a longer time if it is the powder actually, okay, not the liquid, because it will be getting disintegrated. But that problem we don't have with perchloron. Then chlorine tablets are there, which is mostly useful for a small scale disinfection. So under various trade name, we can get these chlorine tablets like halazon tablets, and a single tablet of 0.5 gram is sufficient to disinfect 20 liters of water. So the small can be disinfected by just 0.5 gram of tablet, chlorine tablet, and we get it in different trade names. Then we can use iodine, and that is usually used for emergency disinfection of water. Like we get to know there is a cholera outbreak or a viral hepatitis outbreak, hepatitis A outbreak, and then we go to that particular area, suppose a village or something, and we see that, oh, this is the well from which all the people in that village is taking the water from. So in those condition, because it is an emergency condition, we can use iodine. It will be highly effective than that of chlorine in an emergency purpose. And the problem is, one thing, it's high cost. Bleaching powder costs very less actually, but if it is iodine, it is going to cost more, and that is not routinely used because it can result in later thyroid dysfunction, either hypo or mostly hyperthyroidism. It is going to happen if we are going to treat always with iodine. So that is why for a routine purpose we don't use iodine for a disinfection, only for emergency purpose. Then another thing that we can use for as a chemical disinfectant is potassium permanganate. Earlier this was used. Earlier this was used because it was effective in killing the cholera vibrio or the vibrio cholerae, the bacteria which causes cholera. But later it was found out that it will only kill only the cholera bacteria or the vibrio cholerae. It is not effective against other type of organism. And potassium permanganate, if you know, when we are mixing it, it will impart a color, a pink color, a magenta color, depending on the quantity that is being used. So it was once widely used, but not longer recommended nowadays. It is not a satisfactory agent for disinfecting water. It may kill cholera vibrio, but is of little use against other disease organisms. And also it is going to alter the color, smell and taste of water. Then for filtration, it can be purified in a small scale by Pasteur Chamberlain filter, Berkefeld filter and Katadyn filter. Most of it you might be having in your house. This also following in a way that principles of the slow sand filtration. You can see that different layers of sand, gravel, etc. Then ultraviolet irradiation, I told you about the UV rays, effective against killing the microorganisms. But advantages, it's for short period, no foreign matter is introduced when we are treating, no taste and odor change is produced. And overexposure doesn't cause any problem also. But the disadvantage is no residual effect, lack of rapid field test to know whether this treatment have been efficient. And moreover, the apparatus is very expensive. This I already told you. Now for the disinfection of wells, because they are the main source of water supply in the rural area. So to disinfect them, sometimes on a mass scale, especially during epidemics of cholera or gastroenteritis, the most cheap and effective method is by using bleaching powder. And put a link, you can watch it later to understand the process of chlorinating wells. Okay, so we'll stop over here.